Are we live? Everybody can hear me. Hello. Good afternoon, good evening, and good morning if it's morning where you're at. My name is John Scavardonis. I am responsible for technical marketing for our plastics in electronics and electrical applications in North America. And I would love to give you a brief tour of our technical center here in Pittsburgh in honor of Engineers Week at Covestro. So we have a really exciting tour ahead of us. It's what I like to call practical magic, where our plastics engineers, experts talk about the way that they solve customer problems and the challenges that they overcome for new application areas. And this is in Pittsburgh, is our technical center for the entire North American region. So what you see behind me and where we will go in a few minutes is the lab where the testing is being done, as well as where all the processing takes place, where our materials are being fine-tuned to deliver the properties that our customers require. Before we get into the lab, though, I'd like to take a minute to explain what Covestro does and how we work with our customers. We strive to make the world a brighter place through all sorts of applications out there, and our two guiding principles are innovation and sustainability. That goes and permeates through everything we do, from products to processes, as well as to our facilities. Now, today we will be touring our Polycarbonates Technical Center here in Pittsburgh, and this houses all of the labs that I mentioned before. Before I get started, a really brief history of plastics. Modern plastics were invented around the early 1900s when natural-made polymers were dwindling and people were looking for alternatives to things like tortoiseshell or ivory or even silk. Bakelite was invented in 1907. Nylon, the first synthetic fiber, was invented in 1938. And we had polyester in 1941, and in 1953, polycarbonate was invented by Hermann Schnell in Bayer's laboratories. This was a truly amazing material. It was, by the way, commercialized under the name Macrolon, which is still our trade name today, and the one that everybody knows, our polycarbonate with the legendary properties. This material was really amazing. It was water clear, transparent, great optical qualities, essentially break-proof. It was shatter resistant. It would hold its shape at temperatures higher than the boiling point of water, and it would be impact resistant down to minus 100 Celsius. It could be flame retarded. It could be chemically stable. It could do all sorts of amazing things. So as you can imagine, there were plenty of applications that were perfectly suited for it. Very first application were telephone receivers, if you remember the old rotary telephones, and also movie film canisters. And then the first commercial big shot application that most everybody remembers are the bubble lights on top of police cars in 1960. If we can play a brief little video, we can talk about other applications that polycarbonate is used in. Can we have that video, please?
Automotive, electronics, food contact, electrical, consumer products, protective gear, medical, household appliances, construction. What do all of these things have in common? The answer is polycarbonate, a high-performance plastic that is simultaneously strong, lightweight, heat-resistant, and durable with glass-like transparency. Covestro polycarbonates go into products that enrich our daily lives, from the electronics in our hands to the vehicles we drive. Polycarbonates can be found in a wide range of industries. Whether large or small, these materials can make all the difference in performance and design. At Covestro, we stand for strong commitment to our polycarbonate products, our customers, and you, our downstream users. Our goal? To make the world a brighter place.
Awesome, my friend Olivia. And those are applications that highlight the three key areas for polycarbonate: mobility, electronics and electrical, and healthcare. Now, as you can imagine, a material this versatile finds lots of new uses. And one of the areas that I'm pretty excited about is electric vehicle charging infrastructure or electric vehicle chargers. And what you have is these chargers that are sitting outside in all kinds of weather conditions. They have to perform well. They have to be, of course, flame retarded because there's a lot of electricity flowing through these things. They have to be really, really tough. The screens have to be protected. So again, perfect application for polycarbonate. Luggage is another application area that I get pretty fired up about because here you need something that's going to be super lightweight and super tough to take all the abuse that luggage suffers as it goes into the cargo holds of planes, et cetera, et cetera. By the way, polycarbonate furniture is really cool. Clear, of course, is the key thing here, even though we added some color to these chairs. And one that I get really pretty fired up about is this little bike, which you notice doesn't have pedals. It's a balance bike for when kids first learn how to ride a bike. And the entire frame is made out of polycarbonate. If you put LEDs inside, all of a sudden you have a really, really eye-catching application. Kids, I know, love this. And they, when they start showing off one of these in the neighborhood, they automatically become a star. A whole bunch of different other applications. I'm not going to get into a lot, but let's just say healthcare we're going to touch upon, electronics we're going to touch upon, and mobility as well. Over here is a really cool application. What you see on this turntable is a helmet for a firefighter, which is used in woodland areas. So think of forest fires, things like that. And here what you're seeing is the visors. There's two of them that come down and protect the face of the firefighter as well as their eyes. They have to take impact, of course, for all sorts of flying debris, and they also have to take a super high temperature. And finally, I mentioned mobility a few times. I'm going to power this up. Mobility is an area where we find a tremendous number of applications. From headlights, now just about every car on the road now has polycarbonate lenses on their headlights, to exterior trim, to sunroofs or glazing, parts that we would normally call windows, other than the windshield right now, side windows, things like that. And then if you go inside the car, you got the instrument panel, you got interior trim, and then you have screens. You have screens all over the place. Those screens also incorporate polycarbonate. And we're going to talk about a little later about some really cool technology that's coming out right now to make those screens even easier to put in all sorts of different applications. I think it's time for us to venture towards the Applications Development Lab. And you may be wondering, what is application development? So I think we have another video to play that gives you a very brief introduction to applications development. Can we play that video, please?
World-scale production sites, innovation centers, color and design facilities. Covestro is a renowned global leader in polycarbonate and PC-based solutions with an extensive network of capabilities. At Covestro, we strive to be the go-to partner for our customers' existing and new applications and pride ourselves on exceptional technical support. From concept development to optimizing applications, our product experts work closely with our customers at every stage of the product cycle to achieve the best results from Covestro polycarbonates. Covestro's vast knowledge in cutting-edge molding and processing tools aids in providing customers extended alternatives for manufacturing components.
All right, I think I'm back. Yes, I am. All right, before we go in, let me remember to put on my safety gear. Safety glasses are required. I can put my glasses away somewhere. And we will venture into our high bay area. All right, now what you see in here are a bunch of large machines, processing equipment, as well as equipment that dries the polycarbonate. We'll get to that in a minute. But as we're walking over to the molding machine, what I wanted to point out are the lights in the ceiling. High bay lights in this case, and lights in general, are a big application area for our polycarbonates, again, because they have glass-like transparency. In addition, a really exciting part of the light engine, if you will, is that it puts out heat. And traditionally, you would need a heat sink to pull that heat away from the LED and the circuit board to prolong the life of those electronics. In the case of the lights up there, what we're using is thermally conductive polycarbonate that actually pulls away the heat very efficiently and makes the entire assembly much, much less heavy. So it's very lightweight, and it's also plastic. So you don't have to worry about, at the end of life, trying to separate metal from plastic when you're trying to recycle. Really important application. Let's go over to this molding machine over here. My colleague Jessica is going to take over, and she's going to give us a basic intro on molding. Jessica.
Hello, everyone. Thank you for joining us today. I'll be talking about injection molding 101. So how do we actually turn our pellets right here into an actual part that I'll be demonstrating today and explaining further. So here at our R&D facility, we actually have to test our material properties. All of our customers in healthcare, mobility, electronics area have to have a certain specification for their products. So for example, it has to be an impact, thermal, and electrical. Especially for electrical, you have to have a flame retardancy so it doesn't burn up in your house, for example. So right now, what I'm going to do is I'm going to take you through the entire process of how we're going to make a pencil bar. Like I showcase here, a pencil bar is actually what you pull, and it shows you how the strength and toughness of material that we're going to demonstrate here. So before we get into the process, we always want to be safety first. We always want to protect ourselves. Always have to have our safety glasses on, steel-toe shoes, and our gloves. So to first start off, polycarbonate is a hydroscopic material, which means that it absorbs water very well. So if we turn around here, Andy, we have a bank of dryers, and with these bank of dryers, we actually place our pellets into them, and they dry the material at a specific temperature and time so they're nice and dry before the injection molding process. If we can take a closer look, I'm going to take that off. You can actually see in the dryer, we see pellets in there that are drying right now. I'm going to go ahead and grab my little cup. I'm going to pour some pellets into it. And I'm going to walk back over to injection molding machine. So basically what I did is I placed the pellets into a hopper, we call it. Now it's time to turn these pellets into an actual part. So Andy, if you want to step in here. So we're taking a closer look into the injection molding machine. What you see here is basically called a heater band that's surrounding a barrel with a screw. This is what a typical injection molding screw looks like. So basically what we do is we have a heater band. With polycarbonate, we actually heat up this entire barrel to around 550 F. But with different materials, you can range from 400 F all the way up to 600 F. So what we do is we actually convey the pellets, turning it, so we're compressing the pellets, we're shear heating the pellets, and adding temperature into it. So when it comes out of this nozzle right here that we showcase here, you're actually going to see what looks like kind of goo, like almost like silly putty, right? But we actually call this in the injection molding world purge. So what I'll be demonstrating in a few seconds is how it comes out of the barrel, how it comes out of the nozzle. So I'm going to open it back up again. And if you want to take a little bit closer look right at the nozzle, you can actually see how homogeneous that the pellets are right now. So now we're ready to actually begin the injection molding process. So before we get started in molding the parts, and you want to come over here, I'm going to explain to you, this is called an injection molding tool, which is typically made out of steel or aluminum. So what we do is we actually send the part or a CAD file to an expert, and they're able to manufacture this tool for us to actually make the part. Now I'm going to step aside and we're going to make one part here. So now if you want to take another look around here, it's very difficult to see through the glass. But what we're doing right now with the tooling is that we create a clamp tonnage. And the reason is that this machine has about 100 tons of clamp tonnage on it. And the purpose of it is that in an injection molding process, it creates extreme pressure. So we can see pressures ranging from 5,000 PSI all the way up to 25,000 PSI. So that's why we have to make sure our clamp is closed. If it's not closed, you can actually the plastic can actually open it up and cause damage to the tooling, which you don't want to happen. The entire process usually takes about 35 seconds to around a minute, just depending on the part design and the complexity of that part. All right, now the part's fully open. We'll take a closer look at it right now. So right now, I'm going to be pulling out the part and showing you what it finally looks like. Right here. So here's a perfectly part. We can actually take this part now and then do testing on it, which you'll be seeing later in this broadcast. Now, with any type of defective parts, we always recycle them, all right? So we always throw them in the bin over here and we recycle them. So we send them out to another facility and they cut it up into pellets and we can reuse them for a different application. Now, from the engineering side, we always have to put our engineering hat back on. So every time you make a part, it's not a perfect part coming out of the press. So here, I'm going to demonstrate what a defective part is and how we could actually change and manipulate to make a good part. Again, with going through the process, since this takes a little bit of time, I already made a pre-defective part here. You can see it right there. What you're basically seeing and showcasing right in that part, let me move it a little bit around a little bit. You can see it. So what we call this is sink. And sink, what it means to have a sink mark is that you have an ununiform thickness across the entire part, which gives you an optical defect and changes your mechanical properties as well. So what I just pulled out before was actually a perfectly uniform part, nice gloss level and everything. So we'll get to maximize our mechanical properties and their appearance with this type of part. Again, you can take a little bit of a closer look again. It's a little bit hard to see. Hopefully you can see it in the reflection. All right, so lastly, with this, we do have product data sheets. And like I said before, with our product data sheets, we're able to make different kinds of parts. Today, I just basically showed you a tensile bar, but we make different parts for impact properties, electrical properties, as well as on the back of this, as well as thermal properties as well too. So this is what we do. We generate all these properties for the customers and make sure it meets their specifications. Now, up to John. John's going to show you healthcare and how our products are integrated into the healthcare sector.
Awesome. Thank you, Jessica. And yeah, healthcare is a really big industry for us. If you think about healthcare applications that polycarbonate is used in, typical ones are surgical or perhaps respiratory, cardiovascular. One that's really exciting is drug delivery. And we have a short little video that will show you a more recent drug delivery application. Can we have that video, please?
At Pirouette, we've developed a revolutionary auto-injector that focuses on three main pain points: affordability, portability, and usability. And we partnered with Covestro to use materials that are extremely strong, but also medical grade, so that we can pack a big punch into a little package.
And that's it. So we're here. This is a different machine. My buddy Isaac here is going to tell you all about healthcare. Take it away, Isaac.
Hello, everybody. Thanks for coming. My name is Isaac Platty. I'm an application development engineer in our application development group, responsible specifically for technical support for the healthcare industry. So today, what I'm going to be walking through is a little demonstrator that we have that we've created. So we create these for a variety of projects with different industries to kind of highlight and really promote our materials and the different types of applications that they would then go into. So this would be simulating a sort of drug delivery device that's fully operational. So it's spring loaded. So you can see we have a variety of different materials that are in some of the internal components. So some of these would be like the magenta and orange components, could be some low frictional grades for some of the sliding interactions on the inside. The purple component could be something of glass filled for low creep resistance, high strength, for maybe thinking for a drug delivery type of an application for some high bolus types of injections, high viscosity types of drugs that could be implemented into these devices, as well as high flow materials for the housing as parts are continually getting thinner. So what can we do with these types of components? Do a variety of testing that would then be really more application specific to our customers and for our customers for whatever their performance requirements might be. Rather than just utilizing a tensile bar that Jessica just finally molded for us and demonstrated to give us some general data sheet types of properties, we can use devices like this to really give ourselves application-specific data points that are a little bit more applicable to the customer, maybe a little bit more direct into the application that these materials will be going into. So with this device, we're going to be able to test button force activation. So basically the difference in amount of force it requires to push down the device and activate it and actually fire the entire mechanism. And we've been able to show with implementing some of our low friction grades that you can lower the activation force of this device as compared to a standard medical macro line by around 30%. So it's really good data that we have to show that we can then provide to our customers and then bring back the value that is brought about with our materials. Thinking towards the glass filled in here, we can then demonstrate for long-term shelf life studies, setting these devices up and then simulating what it would be like on a transport. These devices would be fully assembled, fully loaded, and then allowed to sit for, it could be up to 1 to 2 years before they're actually being used by the patient. And so our materials are going to have to withstand any sort of forces or loading that would be imparted upon them during that time of duration. We can kind of walk in quickly if we want to see what we're molding today. We're kind of molding the housing component. Hopefully be able to get a good one. We've been having a little bit of machine trouble this morning, so the downsides of doing things on a live stream, but you know, that's life and we'll be working through them. But so we kind of are walking through the injection molding process of this type of a demonstrator. We did design it here locally. It's an internal design to Covestro that we worked alongside a local design firm called Bally Design. And then kind of, we do have a short video that we can show side by side, hopefully, that kind of demonstrates some of what would go on the front end of creating these types of devices. Looking at mold filling simulations, taking these materials, actually simulating what's actually happening in the tool prior to actually constructing the metal and the tooling that we would then get on site. And then moving forward into prototype tooling and then being able to get parts on the floor and then perform these actual tests that we're talking about. So we're really looking forward to bringing this device to more and more customers as we take it to trade shows, take it to customers for internal meetings, and really showcase the value that our materials bring to our customers. So with that, I'll turn it back over to John, and he'll walk through another industry that's really important to Covestro.
Awesome. Thank you, Isaac. And yeah, in fact, I get super pumped when I'm talking about electronics and electrical applications. But what's really, really interesting to me is that there's been a blurring of the boundaries. What we used to think of as just electronics or just mobility or just healthcare is actually all coming together. And what we're talking about now is the smartification, if you will, of applications. You've heard of IoT, the Internet of Things, but I actually like to talk about the intelligence of things. In the future, things will be connected. And that means that even though an application might be healthcare or might be mobility related, there's actually electronics involved. And that's where everything comes together. We're going to have a very brief video of a really cool application, this very futuristic helmet that I'd like you to play now.
This
and
is
then
kind
I'm going to
of
show you our
smart helmet
demonstrator.
for the motorcycle. And it has a back camera and a heads-up display here. And this camera has a capture behind you and kind of like a wider angle lens, and also streaming to the heads-up display. So always you can check behind you. And this concept is like always 360-degree awareness. We're trying to eliminate all of blind spots. That's the first concept. The secondary, it has kind of original noise cancellation system. And third feature is like it has a Bluetooth and a GPS function, so you can pair with your smartphone. So music playback, listen to the radio, phone call with your friends.
Very cool. And I'm also really curious about what materials you use for this and why you decide to use them.
All right. We are mainly using a polycarbonate. Yeah, this visor and the upper shell and the kind of camera lens.
And why did you choose polycarbonate?
Pretty lightweight and durable.
And that is from a couple of years ago at CES, but it still gets me fired up every time I see it. What we've created to showcase these types of applications is what we call the Nighthawk demonstrator. And this is what it looks like right here. It's a very thin device. I can't pull it too much because I actually have it plugged into the power source, but if you can see from the side, it's a really, really thin piece of polycarbonate that embodies a whole bunch of functions. It has the lights that you see. It actually has lights that are projected onto the surface underneath it. It has an embedded screen, which is only visible after it comes on. In other words, it's hidden until lit. And it's got a whole bunch of sensors. So over here, you will see something that looks like a thermostat sensor. It's a simulation. But what we can do is we actually have capacitive touch slider that I can use to change the set point, for example. I would press that, and that changes the set point. On this side, it shows, for example, that you're connected to a Wi-Fi hotspot. You can even have fun simulations like a Starfield simulation going on. Now, the really cool thing that we have here is that this is powered by a Raspberry Pi computer, and the Raspberry Pi computer has no heatsink. What you see here in the base is that it's molded from thermally conductive polycarbonate. Again, we are using polycarbonate for the base. We're using polycarbonate for the top cover. All the electronics are embedded. If you were to find this at the end of life, you would simply pull out the computer chips, the computer boards, and you would be left with just polycarbonate. Really, really easy to recycle. You probably saw Corey when he was injecting the cover. He's actually injecting clear covers right now, just the polycarbonate resin. But what actually we're doing is when we're molding this, this cover is we have films that go inside, one on the front, which is a decorative film, one on the back that carries the electronics, and the polycarbonate resin that goes in between, which is another part that Corey's pulling out right now. And of course, there's a window behind which we will optically bond the OLED display. Thank you, sir. Now let's talk about testing. There's a ton of properties that polycarbonate is famous for that I already mentioned. However, we have to continually push ourselves. We have to continually strive to get to a place where we can deliver more for our customers. And of course, the way that we find out if our materials are actually meeting these requirements is by testing. So what you'll see in the testing lab are a bunch of different devices, instruments that do the testing, as well as we also do teardowns. What we do is we take an application that's in the field, for example, and we'll look at how it's made, what components are in there. Can we show the video of the pendulum? Yes, you're showing it. Thank you. You beat me to it. Pendulum testing, that's IZOD testing, where the material is tough. So you really have to put a notch in it, a stress concentrator, to make it break. And now what we're seeing is a projectile impact. And again, on the left, you see tempered glass. It shatters. On the right, you see polycarbonate. It bounces right off. Boink. So there's a whole bunch of different tests. What we'll do first, I think, is the Instron, where we're actually looking at the toughness. We're stretching the material. And I'm going to walk a little bit faster so we can go into the testing lab. Right this way, please. Colleague Jeff is here, and he's waiting for us. Hello, Jeff. Take it away.
Welcome, everybody. What I'd like to show you now is one of the tests we perform on our materials. And this is a tensile bar, similar to the one Jessica just molded out in the lab on our molding machine. And this machine is called an Instron. So this machine is capable of push-pull tests. And what it's going to do right now is going to show you, actually demonstrate the toughness of our material that we've been talking about. I'm going to go ahead and place the bar into the fixture of the machine. And what it's going to do here is I start the test, it's going to pull the bar, okay? So this test could take a few minutes when we have a really good material. It's capable of, our materials are capable of elongations up to and over 100%. So you've been hearing a lot about properties today, impact strength and optical clarity, chemical resistance. These are all very important things that as designers and engineers you have to consider for your application. What properties in your application what properties are required for your application? So in addition to some of the things we talked about, we have flame retardant grades for electrical applications. We have UV stabilized grades for outdoor applications. We have chemical resistance grades for medical consumer applications. Thermally conductive grades, as John mentioned, for heat sinks on lighting applications. And I want you to also notice how this bar is going now. We're up over 93% elongation. So this is just a live demonstration of how tough our material really is. Okay, and you see right there, it failed at 104% elongation of its normal. I'll show you. So there's the bar that we pulled. And that's what we started with. So I'd say that's pretty outstanding toughness.
Oh, yeah. And actually, this was an accelerated test that you were performing.
Yeah, we sped it a little bit.
For the video.
Yeah, this test can take twice as long because our material is very strong.
That makes it stretch even further. Thank you. Thank you, Jeff. Let's move on to the next station here, where Isaac's going to show us something about how do you bond parts that are made out of polycarbonate. Isaac, back to you.
Thank you, John, and welcome back. Welcome out to our engineering lab, where we have a lot of different joining technologies that, as John had mentioned, that we utilize to do some screening, feasibility studies, evaluate how our materials can be joined together, whether it's welding, whether it's using adhesives, could be solvents, different types of welding techniques, ultrasonic welding, hot plate welding, and what we have here to demonstrate today would be laser welding. So maybe a quick demo or a kind of a background on laser welding. So basically we have laser energy, and our laser is at 980 nanometers. You need to have one substrate that would be absorptive to that energy and one that would be transmissive. So clearly that's the transparent material. We have a black material. Black does work especially well just due to the amount of carbon black that's in the material. That's inherently absorptive to that laser energy, heats up the weld joint, and then we'll then bond the two samples. So you see here I have two samples. And I'll quickly run through a demonstration to get ourselves something like this, where we'll then have a fully joined sample that we can then take over to the Instron machine that Jeff was just looking at, and then look at the amount of shear stress is required to actually break that joint, kind of give ourselves a relative benchmarking with our materials and maybe looking at competitive materials as well. So if you want to bring yourself in here, we can kind of take a quick look at some tooling of what would be required with this. So we have the fixturing down on the bottom that basically is just going to hold these together. This would be where the laser energy is going to be imparted upon the part. So we're just going to place one part in here like this, like that. And then we are going to close the door, so you're not going to be seeing anything, but of course, safety first. We don't want any laser energy being emitted anywhere. This is a very fast process. I'm going to hit the buttons, and then in about 2 seconds, we're going to have a finished part fully welded. And we're all done. We'll bring this out. So you can see I walked in with two pieces, and now we have one piece that's been nicely welded together with the amount of time that we put into it. Of course, this is kind of optimized for a testing sample, but in the real life, you'd be optimizing your amount of time that you're going to be welding it, possibly the amplitude, the amount of laser energy that you're going to be imparting on it, maybe the amount of clamp force and what have you, just to bring about a fully optimized weld. So this is a very simple part, but a really good part for us to be doing feasibility studies and evaluating material performance. So what could we do next with that? And this is kind of taking it to the next step of what we're looking to do with this laser welding machine, is utilizing some internally designed headlamp type of components. So coming back to the thermally conductive, so on the back side, this is a thermally conductive polycarbonate that's being utilized as a heat sink. But then as a second shot, has a second shot of similar material that I was just using in welding to be providing that weld joint surface to have that absorptive energy. And then kind of having the transparent lens being looking at what John had showed us earlier of an automotive headlamp. So really bringing something that's a little bit more customer focused and applicable to a customer in a geometry that is really relevant to them in that sort of industry. So this is kind of generation one of this design that we're then going to be utilizing and be doing some feasibility studies on our laser welder. And then I'm going to move over, we'll take you over to Jessica, where she can kind of look at a next generation design with a little bit more functionality to it. So thanks, everybody.
Thank you, Isaac. We're going to turn it up a notch.
Thank you, Isaac. Thank you, John. Like Isaac just stated, we did up a notch with our headlamp. So one of the big topics at Covestro today is sustainability. And especially in the automotive industry, they're asking us, how can our materials be sustainable? So what we did is we developed a monolithic headlamp. And what that means is that this headlamp is actually made of one type of polymer, which is polycarbonate. So when I go through this, basically we're going to see you have an outer lens here, which is made of our clear polycarbonate. On the back side, like Isaac said before, we have our thermally conductive polymer, which is a replacement for aluminum heat sink. So we can have a polycarbonate heat sink as well. Now in this design, everyone likes the lighting, right? The wow factor. So we want to integrate the wow factor in there. So what we did is we have a light guide that has LEDs behind it to showcase that. We also have different type of diffusion grades to give you that subtle lighting effect. Now what's going to be turning on over here shortly is over here be your turn signal. So we have different types of colors, which is yellow and red on a red scale. Additionally, we're showcasing that for your reflectors, right, you have to have your high beam and low beam that you just showed here, has to reflect off. And that is actually made of our polycarbonate as well. So here at Covestro, we're trying to prototype how can we integrate our material in a sustainable fashion. Additionally, like John said before, we're getting electrified, right? Not just in the electronics industry, but also in the automotive industry. So we're looking at different designs for our front grille. Everyone probably has seen this from CES and from other automotive shows, but your front grille is evolving, is coming a seamless design. So what we're showcasing here is basically we have a blank canvas, right? Clear polycarbonate. What can you do behind the scenes to make it pop with different lighting effects and integration of sensors? So since we're a global company, our team over in Germany actually created this demonstrator. And basically what it is it's including a film, a decorative film, and you can actually integrate sensors that you can see from here. So we have sensor transparency where you see where my hand is. And then you can actually create lighting effects behind it. So when we do some illumination, you can actually see it really pop out there. So that's some of the stuff that we're doing in the automotive section. I would like to wrap it up today and pass it back to John.
Thank you, Jessica. And the key thing that I wanted to say is in conventional vehicles, you have the radiator grille. The radiator grille is required because the radiator cools the internal combustion engine. In the case of an electric vehicle, you don't have that cooling problem anymore. And that area that the grille used to occupy now becomes prime real estate. So you can put in a screen, you can put in the sensors like Jessica was talking about, we can have infrared, we can have LiDAR, we can have optical sensors. And the whole point there is the part might look opaque, the part might look like it's solid, but the wavelength of the sensor actually goes right through. And that's the intent. It's done by design. It's actually built into the headlamp that Jessica was showing. There is a LiDAR sensor built into that headlamp as well. And the intent here is, what is it that the automotive companies want, and how can we elevate the experience for the user? By the way, the front panel, as we call it, can be also an advertisement. You can have branding over there specific to different vehicles with well-known symbols. You can also have communication. This vehicle is talking to other vehicles on the road, or this vehicle is talking to the infrastructure. It's talking to the city grid. It's talking to the pedestrian that's getting ready to cross and telling him it's okay, you can cross the road now. I think that's everything for today. I'd like to wrap up by reinforcing the fact that we got two main focal points at Covestro. One is innovation, the second is sustainability, and essentially everything we do revolves around those two. So I think we have some time for a Q&A, and we have this area set up behind me. I'm going to walk over here. I'm not wearing my glasses, so I'm going to have to get really close to the screen. And Jessica, Isaac, Jeff, you want to join us? So now, did I hear an echo? I do. This is where it's really funny, by the way, because I think there's a delay here. And what we're doing is we're a little bit in the future compared to the screen, to the other screen, the other screen. This, we can have all sorts of jokes about this. All right. I'm trying to read questions, but I can't really see anything. All these technologies, this equipment, Covestro made them, are they licensed by some other company? Any one of you would like to answer that one?
I can take a swag first, then maybe Jessica, if you want to come across. So thank you for the question. Not fully aware of what you mean by technologies, but I guess if you mean the molding machines and stuff like that, of course, we're purchasing those to utilize, and similar to what our customers would be. Technologies in terms of these demonstrators that we've talked about. So in the case of what I was describing with the drug delivery device, and then John was describing with the Nighthawk, those are all internally developed to Covestro, as well as the demonstrator that Jessica walked through, the mono material solution with the headlamp with the TC, thermally conductive polycarbonate heatsink. All those types of, if you want to term them technologies, would be internally designed to Covestro, which we then are utilizing as a talking piece to our customers. So we're by no means a design firm or a product development company who's looking to manufacture devices. We're looking to create demonstrators that then bring about the value proposition of our materials that would then be important to our customers. At the end of the day, that's really the our bread and butter of what we do, especially within application development, bringing these sort of devices and demonstrators and concepts to really show the value that our materials bring to our customers in whatever application that might be.
Yeah, and again, I'd like to reinforce, thank you for that, Isaac. The prime directive for Covestro is we make the pellets. The pellets are sold typically to a molder. The molder molds the parts, and then an OEM or an ODM puts the whole thing together. Right? So there's many different steps in the value chain. And what we try to do is we try to optimize our materials to deliver on the properties that are required for the specific application. I saw a question that had to do with injection molding versus 3D printing. Yeah, there it is. So it says, which is better, polycarbonate or 3D printing plastic? And I think what the user is asking is, which is easier, which is more efficient, injection molding or 3D printing, which I can take a quick stab at it, and then you guys can jump in if you want. My opinion is 3D printing is quick, 3D printing is fast. So if you're trying to do a quick study, if you're trying to do a quick design study, you can use 3D printing. If you're going to scale, if you're going to start molding, or I shouldn't say molding, if you're going to start making hundreds of thousands of parts, 3D printing may not be the right approach. There you need a technology like injection molding that allows you to scale quickly. And that would be my quick answer. Any one of you want to add to that?
Yeah, thanks, John. Yeah, I can jump in there. Echoing John again, I think it just depends on what you want to get out of the application. With 3D printing, sometimes your properties are not as great as injection molding, and we've looked at that internally. So like when Jeff was explaining with the tensile bar, elongation 100%, you might not be getting that with a 3D printed part. Also with 3D printing, it's more on the scale of customizable, right? So you can actually make different pieces to customize for that part. With injection molding is really good for mass production, making the same part over and over again at a fast time, as well as injection molding. You're molding a part within 60 seconds. A 3D printed part could take a minute all the way up to 10 minutes, 20 minutes, 30 minutes. So from that perspective, I think 3D printing is very good for prototyping and small scale, and injection molding is really good for mass production and repeatability.
Awesome, thank you. The questions are really flowing in, and I'm having a hard time even scrolling through them. But I mean, one that actually caught my eye has to do with the software that you folks use. It says, do you use Moldflow or Moldex 3D?
Yeah, we use Moldflow. It's just kind of been historically what our company has used, but we are constantly doing evaluations and looking at optimizations between the different softwares to see if there's anything in particular that could be an enhancement to utilize for our materials, and maybe other features that these softwares could be using, but we have traditionally utilized Autodesk Moldflow.
Excellent, thank you. And then I see one where I'm reading, when 2K or more plastics are injected, extra residence time is required. How is Covestro addressing the thermal stability in PC for lenses and auto applications?
That's a very good question on that topic. Like you said before, due to the complexity and stuff, right? So it's like making polycarbonate is kind of like a recipe, right? You can throw in other different additives in there to make it more thermally stabilized. Additionally, we use a lot of CAE capabilities. So we're basically understanding how long does it take to actually make that part. So when we do so, we know that we have to pick the right type of injection molding machine, the barrel size, to make sure that we're within the limits of the polycarbonate. So that's how we're addressing it, right? So you have to do all of your homework up front before you actually do the molding of the part.
Thank you, Jessica. That's actually right on. Is there, one more question, is there any non-destructive method you use to know properties? Infrared? I don't know. Perhaps.
Yeah, I guess some non-destructive would be, looking at optical transmission. That would be something. But a lot of the times we're kind of looking at mechanical performance. So a lot of, and the properties of polycarbonate that it lends itself well to would be like, we've looked at elongation, we've looked at toughness, we've looked at impact. So a lot of those types of properties require some sort of destructive test. Even looking at evaluating FR grades, that would require some sort of flammability test. So you're going to be burning it and looking at the characteristics there. So probably optical transmission. I don't know, Jessica, if there's anything else that you can think of.
I would think of more of optical transmission, infrared transmission, also a lot of weathering. We do a lot of weathering with our materials. So we have exposure out, maybe simulating a Florida weather or Arizona weather that's non-destructive. And we actually see how our performance is, how the light transmission looks. So sometimes over a long period of time, you can see haze and yellowing. So basically, we have to assess the material to see how long it will last before it does change its color and its haze.
Yeah, and on that note, I'm going to say also polarized light. Polarized light is really useful for visualizing strain, stress inside molded parts. I find it exciting just to see those parts because of all the colors and the interference patterns and everything else that show up. As I was scrolling through here, I saw one that had to do with asking about clean room for medical applications. Jeff, is that something that you can talk to or at all?
Sure.
I don't know.
Yeah, so definitely in production atmosphere, you would be in a clean room for producing medical parts. Here, we're at an R&D facility, so we don't have that capability. But yeah, for sure, in production, it'd be a total. They have filtration systems, controlled environment, temperature, and all that.
And
and add on to that as well too. Back in the day, optical discs, right? CDs, DVDs, etc. was a big thing. So we actually did have a clean room once in this facility, but we don't anymore. That was a big thing to make sure that there was no dust particles that would be integrated into that type of optical disc.
You took it right out of my mouth. That's exactly what I was going to bring up. If you go to a facility that molds parts for medical, you might see a class 100 facility or a class 10 even. It was also something that was useful for optical media. We don't have that here anymore. There was one more. How are you checking maximum critical shear rate in the lab?
We don't have the capability to check that in the lab. So we would be utilizing external partners to be looking at with like an injection molding rheometer and checking the capabilities of our material. But we don't have those types of capabilities here in-house.
And somebody actually said that Arizona or Florida weather would be ideal for Pittsburgh. Right now, it's a little chilly outside. I agree. But Jessica's wearing short sleeves, and so is Isaac. So I don't know what they're talking about. It's not that cold. One more question about instrumentation: capillary rheometry or lab extruder?
We do have some analytical capabilities to look at like rheometry to kind of check. We typically are utilizing that for checking specifications or checking for thermal degradation from components on parts. Here in our Pittsburgh facility, that's probably a little bit less utilized for looking at production sites. That would probably be more so from our Newark facility or maybe down in Baytown, where they're doing, those are much more full-scale production sites. Newark, Ohio being our compounding facility, and then Baytown, Texas would be more of our wet side production. But here in Pittsburgh, we kind of have a smaller physical testing and analytical lab that we can utilize to support customers that does smaller scale stuff, checking MVR through a rheometer and what have you from there. But in terms of production scale types of testing, that's not going to be here on site.
And I'd like to address a couple of questions from earlier on. One was asking why the masks. That is a mandate in Pennsylvania.